Thank you, Kathy. I mean, it's not only a pleasure to, to participate in MetroFlow, but it's even a greater pleasure to be introduced by you. and yes, I'm very happy that I can't get rid of you. So I'm very happy to continue our, usual collaborations, not only in education, but also, pertaining cell sorting, as I'm going to discuss today. So yeah, what I want to really do today is talk a little bit about best practices, concepts about cell sorting that I think are really useful. So one of the ideas initially was to talk about the future of cell sorting, but there are so many things to talk about. The present of cell sorting and what's going on. Like I said, a lot of best practices, misconceptions, and things like that haven't been really understood and are still very debatable. And so I want to bring up a lot of questions, and maybe we can. This will also spur a lot of discussion in the roundtable. Control my slides. So as I was saying, there are a lot of things, probably you guys, as a lot of the people here that are listening, probably work in flow core facilities, or at least have a lot of experience in cell sorting. And there are so many things that we haven't addressed yet. And we as a flow core facility, of course, we think a lot about cell sorting. And one of the things we've tried to do for a long time is to address a lot of these issues, like double discrimination, thresholding, the importance of flow rate and resolution. How do you do proper post-sort quality control? But these are things that we would like to address in the future. But today, I really want to talk about two topics, which are cell sorter performance, or instrument performance, and the impact of sorting on cells. And before we go forward, I want to ask Kathy if she could pull out a poll, and I just want to gauge a little bit the community, and essentially ask the question: what do you guys think? Jet and air sensing sorters are better in general for recovery yield and viability than cuvette-based sorters? And just pick a choice. Even if you don't know, just say you don't know, or answer to any of these questions. I don't know. I can't vote, so I'm not allowed. So maybe, Kathy, I don't know if should we give it a few seconds?
Let's give it a couple more seconds. You have some people still answering, 62 out of 145. So nice. I will end the poll when we get to about 50%. Oh, we're there. Mm-hmm. So let me launch those results.
Okay, so we get, so we have 29% saying it's true, 17% saying it's false, and I guess the majority doesn't know. And some of you answered all the above. You don't know, it's true, it's false. So very nice. And I'll keep this, in mind, because I'd like to come back to this at the end of the talk and discuss. But again, there has been a lot of anecdotal evidence on, the impact of cell sorting on cells, the fact that maybe jet and air sorters are better. I mean, this is a conception, or this is a concept, sorry, that has been lingering for many years. But nobody has really addressed this on a systematic basis and has actually answered the question. Now, have they or have they not? So this is what I want to try to see today, and see if I can discuss this with you guys. So let's start with the history of cell sorting, just to give you kind of an overview of how cell sorting came about. And actually, I put here the history of flow cytometry because, as you can see, the history of flow cytometry actually starts with cell sorting. So in the 1960s, Mac Fulwiler developed the first electrostatic cell sorter based on a few of the inventions that had happened in the same year or the previous year by Louis Kamensky, who was at IBM, and Myron Melamed, who was trying to, here at MSKCC, trying to distinguish between cells from healthy patients versus cancer cells. And they developed a spectrophotometer, and also an invention by Dick Sweet, who invented the inkjet technology, as we know, and that was used by Mac Fulwiler to develop a cell sorter. Now it's interesting that I'm glad that Mac Fulwiler wasn't really a biologist, because I think if you really think about cell sorting in the process, you're how do you say, you're throwing cells into a cell sorter, you're pressurizing them with a pressure that, if you think of 70 psi, think of a car that has, the tires of a car are probably between 30 and 35 psi. And if you've tried to press the tire of the car, you can see how hard it is. And this is what we call a gentle sort in droplet cell sorting. So you put them through this kind of pressure. You run them through all these tubings. You then charge the drop, so you electrocute the cells, and then you throw them with a huge speed inside a tube, and you expect the cells to live, right? Again, any biologist would say this would be impossible, forget it. But luckily, Mac Fulwiler wasn't really a biologist. And so he said, why don't we try? And it actually worked very well for lymphocytes. And it's great because immunology and flow cytometry co-evolved since then. It was just a few years later that Len Hutzenberg added an arc lamp to this electrostatic cell sorter, which was pretty impressive, and coined for the first time the term FACS for fluorescence activated cell sorter. So after that, in a conference in Pensacola, Florida. By the way, a lot of places you'll see that it says 1978 that this conference took place. It's actually not correct. Again, some of the misconceptions that are out there and are very hard to correct. And myself, I was corrected by Howard Shapiro himself, and so since then I've made sure to put the right information here. But anyway, so by then there were about 13 publications on flow cytometry. The term flow cytometry was coined during this conference in 1976, and after that, as you know, the rest is history. The number of publications we have nowadays, for instance, just an example here at MSKCC, just every year the papers that have data of experiments done here in the flow cytometry facility, we have probably about 500 to 800 papers a year just at MSKCC. So you can imagine the amount of papers out there where flow cytometry is being used. So very common. And the most interesting thing that I want to point out here is that although maybe from the 60s to the 90s or the 70s to the 90s, there was a lot of development in terms of performance of cell sorting. The thing is, the actual technology that was developed from the beginning by Mac Fulwiler was so impressive that think of the MetroFlow legacy at the late 90s or the Fax Vantage. We haven't really seen a dramatic or any significant improvement in performance of sorters since that time. Of course, we've seen, we have more lasers, they're smaller, the electronics, detectors have improved, these kind of things. But in terms of performance, speed, yield, purity, we're still the newest, the latest. Look at Bigfoot from Propel or Thermo Fisher. Look at the the Aurora CS from Cytec. Look at the S6, the Fax Symphony S6 from BD. Look at the SRT. Look at Sony. You can start looking at all these instruments, and in terms of performance, they're still on par with what the MetroFlow and the Fax Vantage did back in the day. So really impressive technology, but yet there were a lot of anecdotal concepts that that started becoming mainstream and now are very hard to address, namely the performance, for instance, of jet and air versus cuvette sensing systems, but also the actual performance of the sorters, how they sort. Are they having any impact on cells? We always think of sorters as a very harsh process treatment that we do to our cells, right? Although this technology has been impressive, there are some limitations of droplet cell sorting. One of them is that, yes, they do require a sheath. So you have to dilute always the cells with some sheath buffer, which can dilute the sorted product and can interfere. And actually, I'll show some data from Camilla's paper on the impact of cell sorting on cells. So they can be harsh. Again, like I said, we're putting these cells under so much pressure, literally, and we're electrocuting them, etc. It's really impressive that these cells are still functional, etc. And then the other thing is the efficiency. As I mentioned, we are limited by the natural laws of Poisson statistics, and that's why all of the sorters, or the electrostatic or droplet cell sorters, depends on how you want to call them, until now have similar performances, exactly because they are limited by the natural laws and not by technology itself, right? Let's talk a little bit about cell sorter performance. Now, I know that, again, most of you do know how a cell sorter works, but I just want to make sure that everyone is on the same page. So again, you know that cell sorters have sheath running through them, or droplet cell sorters have sheath running through them, and there's a transducer that's sending a sound wave all the way down through the stream, shaking it and breaking it up into droplets, right? So if you have a cell of interest going through the lasers and it's identified as a target cell, then what the system does, it waits until the cell reaches the drop breakoff point, and then it charges the stream. So again, we're electrocuting at least the stream and possibly the cells, and then the droplet breaks off and it uncharges the stream. So only the droplet that contains the cell of interest is charged, right? So once that drop goes through the high voltage electric plates, it will be deflected. So only the droplet, and in this case, oops, it missed the tube. Something went wrong with the animation, but it's a good point for what I want to talk about today. But anyway, so the droplet is deflected, hopefully into the right tube. How do we know, again, looking at this, how do we know whether we're actually sorting the right population? Or basically the question would be, how do we know that your sorter is charging the right drop at the right time? Now, I can tell you a lot of anecdotal evidences or situations that we've seen. For instance, there was a case in many years ago when I was back in Portugal, where we were sorting for one lab, and one of the persons in the lab was sorting B cells from lymph nodes. They had amazing recovery and purity. And then on the same day, like right after, we would sort with the sort in the same conditions. We would sort for these other people from the same lab that was sorting B cells, but from the peritoneal cavity. And the recovery was a disaster. It was like 30 to 40% maximum. We tried to troubleshoot the sorter, and it really made us think, I thought I knew what I was doing, and I kept telling them, look, I've configured or calibrated the instrument the best I could, and I just sorted for a person in your lab, and I sorted B cells, and they said that the recovery was amazing. I mean, they measured, they counted the cells, and everything was impressive. So something is going on with maybe your sample prep, maybe with the centrifuge that you're using to resuspend the cells, or your counting process. So we went through all of this, and everything seemed fine. Now, the interesting thing is that every time I told him, look, I'm pretty sure that the instrument is well calibrated, but at the end of the day, I wasn't really 100% sure, right? And my question to you guys is, how do you know if you're charging the right drop at the right time, right? So the gold standard for measuring sorter performance has been for many years purity. This is of course, if you're sorting for purity, you need to measure purity, but it is not a good measure of the instrument performance, the sorter performance. And here's an example of how many times have you been confronted with this situation. You go to the cell sorting facility, you sort your cells, and you're really happy with the flow core facility. By the way, we get a lot of chocolates at Christmas because people are really happy because we always give them great purity. And cell sorters, I should say that a droplet cell sorter should be sorting with 99% or more purity. If not, there's something wrong either with the sample or with the instrument, right? But that's what it should be performing because it's very precise. It's very good at charging precisely the drop at the right time. But you have to calibrate it and configure it accordingly. So as I was saying, how many times did you look at your samples and the purity was amazing, but then you go back and count your cells and hey, you have much less cells, your recovery is terrible, right? So this got us to think about what could we do to really understand if the sorter was performing well or not. And we started thinking, doing schematics, where are the cells being lost? Where is purity being compromised? And, long story short, I've shown actually this diagram several times in other talks, but, essentially, yeah, cells can be stuck in the tube or even die in the tube while they're waiting. They can die or get stuck in the tubing as they're injected into the system. You can have problems with detection or electronics that are compromising purity or recovery. You can have fanning, etc. But the point here is that if you look at all these processes where you can have cell loss or purity is compromised, every situation where you compromise purity, you're also compromising your recovery, because essentially if you're not sorting the right cell, if you're sorting the wrong cell, that's because you're missing the right cells in the first place. And there are situations where you just lose cells without compromising recovery. So everything was pointing to recovery rather than purity as an assessment of or as a metric to assess instrument performance or sorting performance. And so in an amazing collaboration that we had with several flow cores in Europe, we started thinking about this, and we developed a method called Rmax that some of you probably know, and I won't go into many details because this has been published. But the idea is that if you want to understand if the sorter is charging the right drop at the right time, every time it misses, you're going to sort either the wrong cell or you're going to sort an empty drop, right? So you're going to compromise recovery. And we wanted to, if you look at the center stream, let's say you sorted all of your cells of interest, your target cells. Then you should have 0 target cells in the center stream catch, in the waste, correct? So if you have anything in the waste, it means you've lost those cells that you wanted to sort. And so that was the idea behind this. We did the math, and the assumptions again are based on the fact that anything that you sort will either fall in a sorted tube or the waste. You do the math, simplifying things, you end up with a relationship where the maximum recovery that you can expect in your sorter is dependent on the original ratio of non-target cells and target cells in the original sample. So that's a given. You always record this, before you start sorting to be able to identify the populations that you want to sort. And also dependent on the ratio of target and non-target cells in the waste stream. And And so essentially, if you want to understand if your sorter is well calibrated, all you have to do really is grab some beads. In this case, some calibrite beads. Could be any fluorescent beads. Here, for instance, we have FITC and APC beads, 50-50 ratio, where essentially you can choose which one you want as a target bead. We chose FITC, and then what you do is you start sorting and you collect the center stream rather than the actual sorted droplets, right? And then you reanalyze this on your instrument, and as you can see, again, if you would have perfect recovery, you should see 0 events in the center stream, right, of the target events. You should only see APC beads in this case. So if you see something, it means you haven't recovered everything. And so, you plug these numbers into the formula, you do the math, and you end up with something like 0.953, which means that your maximum recovery under these conditions, under these particular conditions, is 95.3%, which I have to say that anything between maybe 85 and 95% is pretty good. Means that your instrument is sorting the right drop or charging the right drop at the right time. Now, we can use this, for instance, for daily QC to assess our drop charge delay. If you have an ARIA, you use AccuDrop, and how confident are you in whether the AccuDrop has measured the actual time between the lasers and the break-off point, right? So don't assume, and this is very important, don't assume that whatever instrument comes to your hands that everything is working fine. Not only from the vendor, from factory, but also as time goes by, on a day-to-day basis, a lot of things can be happening that you are not aware of, and so it's very important to understand whether the calibration or the QC that you're doing is correct, right? And so if you're so concerned about, for instance, the performance of detection, you should be also very concerned about the performance of your drop charge delay, right? And there's a lot of information out there. Actually, I have to say that we used to have this in an old website, and we will be placing this on our website at MSKCC. So look out for that. Probably in the next week or so, we will have a lot of information on Rmax there to help you out if you need. Now, for me, the important thing is that, okay, you can say, well, I'm confident that whenever I do the AccuDrop or whatever the IntelliSort or, in the other instruments have different ways of determining the timing, the drop charge delay, you could say, well, I'm pretty confident. So why do I need to validate? Well, the first thing is, the same way you validate a biosafety cabinet independently, or the same way you validate with your own internal QC the optical performance of the instrument, you should be also validating the performance of your sorter, right? In terms of charging the right drop at the right time. Now, the thing is, we, again, based on some anecdotal evidence, we started using Rmax to actually check performance of our system, for instance, for particles of different sizes. And this was an impressive work done by Claudio Bispo and Claudio Andrade that, it's very, these plots here summarize many weeks of work, and actually just this experiment took a whole day to be able to do. And actually you can't see here the replicates, but there are replicates for each data point. Now the idea here, what we were doing is, so we're looking, these curves are the curves of the maximum recovery. So we measured the timing, right, the drop charge delay for a MoFlow and FX ARIA 1. And what we saw is that, well, at least for a MoFlow, regardless of the size of beads, whether they were small, 1 micron or 10 micron, that the maximum recovery was exactly matched to the drop charge delay that we had calculated with the vendor's recommended way of measuring it, right? So we were pretty confident that, hey, not only we're measuring correctly the drop charge delay, but also there's no impact between different sizes of particles, right? Regardless of the size of particle, as expected, we should be okay. Then we look at the area and we were surprised, or maybe not as surprised, I don't know, because the, this being a lot of anecdotal evidence is saying that jet and air are different from cuvette-based systems. And so this is very tempting to say, oh, there we go. Do you see? One performs better than the other. Now, it's very important to be very cautious when people state these things, because we're comparing two instruments, one versus another. Although we did a lot of replicates, maybe this instrument is not functioning well. Maybe we didn't know how to calibrate it properly. It's statistically has no meaning at all. So we shouldn't jump to conclusions. And unfortunately, a lot of people do that, and then we end up propagating misconceptions and that become a myth. And so, looking at this, we were quite intrigued and quite surprised to see that if we measure the AccuDrop, depending on the size of the particles, we would be missing the drop altogether. In fact, if you look at this, for this time, for this drop charge delay, we're actually losing 20%, so only recovering 80% rather than 100%. The other thing I would like to point also is the fact that you look at purity. So remember, I mentioned purity is not a good measurement of sorter performance. Look how, and hopefully you see the numbers well. So here it goes from 36 to 37, so a whole drop, as well as here from 41 to 42. So you can span a whole drop difference, change the drop charge delay, one whole drop, and purity is still impressive. It's still pretty much 100% all across the board. But if you look at recovery, as soon as you start moving away from the correct drop charge delay, you'll start seeing an impact on recovery, right? So again, we wanted to start looking at recovery to be able to determine whether these instruments were performing well. We were very surprised with the ARIA. We didn't have an explanation for that, but we also didn't have any statistical meaningful data to be able to do any comparison. So fortunately, when I came to New York, Jennifer Wilshire, that was here before me, had actually already presented some data looking at big particles or bigger particles compared with smaller particles, and they were seeing differences. They were seeing losses of cells, especially as you had bigger and bigger particles. And in a cancer center as ours, it's very easy to actually see that, especially with the number of sorters we have. Now, again, another impressive collaboration that we had here with a lot of amazing flow cores in New York. We put our efforts together. We came up with a common protocol that everyone would use. And again, we used Rmax to evaluate. And I apologize, I don't know if the plots are too small, but essentially to also summarize this, we started looking not only at laser time delay, but also at the drop charge delay of these instruments. And we could see that for some fax areas, not all, for some fax areas, and it only happened with the fax areas, if you were trying to sort or analyze larger particles than the particles that you use to calculate the drop charge delay, that the laser delays were completely off. And the drop charge delay was also completely off. And in fact, we can see here as so we have 7 micron beads, these are 15 micron beads, and these are 19 micron beads. And we did also for 30 micron beads. But essentially what you can see is for the fax, or for some fax areas, we saw that the actual drop charge delay was more than 1 drop away, which was quite significant. So we were losing completely all of the cells or most of the cells that we wanted to sort. And in fact, if you look at this, we're about 50% recovery here. So completely off. And we're talking about 20 micron or 19 to 20 micron beads, particles, which is not a big size for a cancer cell, right? So we were pretty worried about that. Now, fortunately, it happened that this was so obvious that it happened that all of the areas that were giving problems were actually areas that had the rectangular flow cell. And there were a couple of areas that were giving the same results as we saw with the MoFlows, with the influxes, etc., where there was no impact, regardless of the size of the particle. Everything seemed to be fine. Maybe, you know, a slight difference, but, you know, that's expected across, you know, every person, every day that you determine, there's always some slight error there, right? But the point here is that when we looked at the flow cells, we saw that the square cuvette was actually performing very well versus the rectangular. So when we approached BD, we were surprised to know that, oh yeah, they were pretty well aware of this problem. And we questioned, so why are you still selling these flow cells? And I have to say that these flow cells are still being sold. But worse than that is that every facility that actually asked BD to change these flow cells, BD came back and mentioned that, yeah, sure, we'll charge you, I don't know, $20,000, $30,000 per flow cell to change, when in fact these flow cells are changed on a regular basis if you have service contract. So it was very surprising to see. And, you know, I'm not saying anything, I don't want to you know, trash or say anything bad about all the professionals that work for BD. You know, all of the people I know from BD are amazing professionals, amazing people that do their best to give us, you know, the best quality technology. But as a company, I have to say this publicly, that BD really fell short because imagine, in a cancer center like ours, notice the impact that for years we've been losing so many cells. The impact that this has had on reproducibility, not only in cancer centers, but in research in general, and the impact that this has had for people's lives. If you think of, you know, translational research, this is huge. This is huge, and BD really dropped the ball again as a company. And this, you know, the minimum that we would expect would be a recall of all of these flow cells. But not only these weren't recalled, but like I mentioned, they actually charge to replace. So I would just leave it out there that if you do have a rectangular flow cell and you don't have you know, a proper response from the company that's produced these flawed flow cells, it's basically, if you go to a car company, you have problems with the brakes, and the company says, sure, we know it's flawed, but we'll charge you tens of thousands of dollars to replace the brakes, right? So, you know, if you don't get the proper response, please reach out to us, to me, and everyone that's been involved in this work, and we'll try with you to reason with BD. Because to be fair, a lot of the people from BD that are involved in these decisions are not even aware of the impact that this you know, these changes has had. But, you know, the other point I want to make is that you know, think of the fact that these instruments that we thought were functioning or performing perfectly well, you know, according to the vendor, were actually not performing. So again, like I said, any new sorter that you have, you should validate it and make sure that it's working well for any type of particle, right? So let me move on to the second and last topic here, which is the impact of sorters on cells. So how many of us have heard of the, you know, again, the harshness of cells, of sorters on cells due to the pressure? There's even a term that Peter Lopez introduced, 6 sort-induced cell stress. And, you know, this is not the only impact that a sorter can have on cells. Now, I want to show you several papers on that have assessed on a systematic way, because we do hear a lot of anecdotal evidence, but anecdotal evidence is anecdotal, right? So we want to make sure that we don't interpret things based on anecdotes, but rather we have to systematically address things. And I don't want to, I know I'm running behind, running a bit short, so I'll go through. I just want to highlight the most important things here in these papers. So, for instance, this was a great set of experiments that were published recently by Camille and Peter Lopez lab, where they basically looked at Jurkat and 3T3. So again, robust cells and also cells that probably are not as robust, or at least we believe are not to be robust. And the conclusion essentially, so I should say that they used a dual head, where they basically had one head of one of these Sony sorters with PBS as sheath and the other one with RPMI. Now, the conclusions were, looking at metabolism, is that the sheath that you use can rescue the sorter-induced cell stress, right, 6. Now, one of the problems with this experiment, and again, is not to say anything, again, I encourage really to read this paper and interpret things yourselves, but one of the things for me that was missing here was a PBS control, so a non-sorted PBS control, because based on all this, and if you see here, this is a summary of the data where, looking at principal component analysis, you can see that the PBS conditions where sheath was used as where PBS was used as sheath, they all cluster away from the controls and the experiments done with sheath as RPMI. So this kind of gives an indication that, yeah, if you use RPMI as sheath, you can rescue the sort-induced cell stress in this case. Now, like I said, the thing is, since there was no comparison between a PBS resuspended cell sample that wasn't sorted, we could conclude that actually the only differences that we're seeing here in terms of metabolics or metabolism is the fact that the cells resuspended in PBS actually have a different metabolism than the ones that were resuspended in RPMI. So it had nothing to do with the sorter, but just the fact that, and this we also know, even if it's anecdotally, that every time you resuspend cells in a different media than their physiological environment, it's always going to impact. So if you're comparing something resuspended in RPMI, which is much better for the cells, and that's what we do to keep them happy and alive, versus PBS, you may see already differences in metabolism. And there were several other studies out there. So if you think that there aren't any systematic studies on the impact of cell sorting on cells, take another guess. This was an amazing study, also very comprehensive, where Andrew Box, other people, including Peter Lopez also, that did this study, where they looked at, so these are a lot of facilities where they looked at Jurkat, embryonic stem cells, B cells, and they used a lot of instruments, and also several readouts, including microarray analysis. And the conclusion was, and if you look at all of the studies that done the systematic studies on the impact of cell sorting on cells, you'll see that the common conclusion is that cell sorters have little or no impact on the readouts. In this case, it's cell cycle or long-term growth. They saw that there were slight differences in the short term between 0 and 4 hours after sorting, but after that, there were no impacts at all. And there was no impact on the transcriptome. And actually, but even better, if you look, and this is just one of the plots that they have, if you look at one of their TISNI, where they're looking at quantigene assays to validate the microarray data, when they actually cluster things clustered in terms of sites. So notice that no differences between ARIA's influx, MoFlow, so cuvette, blah, 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 nothing. It actually clusters in terms of sites. So again, and this is from their paper, the data suggests experimental noise from sources such as cell health or handling may have a larger influence than the sorting system themselves. Thank you, Kathy. I'm almost there. Give me 2-3 minutes. And this is another paper. So for me, this is one of the most important papers, where again, very good systematic approach. And actually here, they not only they use the control of sorted, unsorted to compare with the sorted samples, but they actually also did a microarray analysis of the samples before they were processed. And this is very important because this allowed them, they looked at all of these types of cells that could be very fragile. And again, the conclusion is from microarray analysis demonstrated that FACS causes minimal disruptions to gene expression. And how cells are handled following isolation seem to be much more critical to obtaining accurate cell lineage gene expression data than one's choice of cell sorting technology, right? Again, no impact of the sorter itself, or very minimal compared to actually the sample handling. So, and again, for the sake of time, we ourselves were worried about, but maybe we haven't been testing the right cells. Maybe there are cells that are much more fragile. We did a similar study, not a systematic study, so this is very preliminary. And I won't even mention which sorter because it's not fair when you're looking at preliminary because it's anecdotal. But we did test the impact of sorting on mouse prostate cells, primary mouse prostate cells, so very fragile or at least sensitive cells. And again, the conclusions were, we did replicates several days. We look, the first state looked promising towards the microfluidic cell sorter, but actually, if you look at the rest of the data, nothing really changed. It was relatively, you got the same recovery, viability was pretty much the same. And when we looked at single cell sequencing, there are some differences between the ARIA and the microfluidic sorter, when compared to unsorted, but they're both slightly different from the unsorted. So one actually enriched more towards the immune subsets, the ARIA, and the microfluidic cell sorter enriched more towards basal or mesenchymal cells. And so again, not really much of an impact. And these are operated at less than 3 psi. These were operated around 12 to 20 psi. So no impact. And the big difference is that here, anything we did, here we sorted everything within 5 minutes compared to the microfluidic sorter that took about an hour. But again, in terms of viability, we still maintained the same viability. So no really impact. Now, am I saying that microfluidic sorters are no good or we don't need those? No, again, this was, every time we present a study, we have to think of it, it's a study done in those conditions, right? So, and there are other advantages. So for instance, biosafety, there's no aerosol formation. You have disposable microfluidic chips. So if you think of clinical sorting is even more important. So yeah, definitely there's a lot of room for microfluidic cell sorters in the market. But when it comes to the impact of inducing stress, this is very questionable whether this is really needed, at least for the cells that for now have been evaluated. And again, I would be very hypocritical to say that no, the sorters don't have an impact on cells, because we actually have published situations where, in this case, these were insect cells, where we couldn't, if we sorted them, we would lose, the viability would go from 95 to around 10%, and we could recover that viability by adding pluronic either to the sample or to the sheath, right? So it does impact, the sorter does impact in some circumstances to some cells, but we need to be able to evaluate this. And this is my my last slides. So just as a summary, of course, the in terms of cell sorter performance, the points that I'm trying to drive here are, do not assume that the vendor instrument performs as stated. You need to validate that. You can use Rmax or any other tool to assess and validate the sorter performance, and even to use it to troubleshoot any issues that you have. In terms of impact on cell sorting, again, most of, if not all of the systematic studies that have been done looking at the impact of cell sorters on cells have seen very little or no impact. And I would say, except maybe for a few cases when we're looking at metabolism, but metabolism may change just because we're changing the conditions in which we were suspending the cells, nothing to do with the sorter. And that remains to be really addressed, again, in a systematic way. So the evidence points to sample preparation and handling as a major contributor to the impact of sorting, so not the sorter, but the sample handling of the impact of sorting on cells, right? And so I just want to finish up with something that we've been thinking a lot about, and I've been discussing with Kathy about this. We need to come up with a systematic way of addressing the impacts of sorting on cells, right? And so we started thinking of something like similar to the MyFlow side, and again this is just ideas that we're rolling out. I called it MyFlow sort comparison. Where it would be important, if we want to start doing these comparisons, we need to have a consensus on what we're measuring and how we're measuring, like what are the readouts that we're using. So we need to specify that very well, the sorting conditions, the sample preparation, the downstream applications, and especially sample preparation. And I just finished off with, how amazing Kathy is, and we were rolling out ideas, and I said, oh, Kathy, I want to show this on the presentation at MetroFlow, and if you have any ideas, just let me know, write them down. 5 minutes later, she just sent me an email with all these things, and I'll leave them here because this session is being recorded and you can take a look at all these things. And as you can see, she came up with loads of stuff that she's been thinking about, and I'm looking forward to continue collaborating with Kathy, and I welcome anyone that wants to also join us and come up with a series of guidelines for these kind of comparisons. And thank you very much.
Thank you so much, Rui. That was an absolutely wonderful talk. And we definitely had some questions come through on the Q&A. Lucky for us, we're going to have you join us at 1:10 for the roundtable conversation. But thank you so much, Rui. That was wonderful.
Thank you.